Hello. I know most of you are still just on your way home from school, but I am doing this at the only time I have the opportunity to today. So there we go. Let's make sure that we are, okay, good. Now, let's take a look at our relevant equations here. One for pendulum and one for springs. Now, the one we're going to use the most there we go, a little bit better. The one that we're going to use the most is, for each one of these, is our period equation. Okay, so now take a look at these two equations. Both of these tell us the same thing. They tell us the period. So for the pendulum, we have our period is equal to 2 pi times the square root of the length of the pendulum over the acceleration due to gravity wherever this pendulum happens to be. Now, the things that are in this equation are period, length, and the acceleration due to gravity, which means those are the only things that matter to this equation, that change the period. So the length and the acceleration due to gravity are the only things that change it. It doesn't matter how much mass is hung from the end of the pendulum, and it doesn't matter how far you pull the pendulum to the left or right. Okay. Next, let's see if we can predict how changing each thing will change the others. So since our length is in the numerator in our fraction, a greater length will lead to a greater period. So the longer the pendulum is, the longer it will take for it to swing through its entire cycle. Next, since our acceleration due to gravity is in the bottom, the bigger this gets, the lower this gets, which again corresponds to the stronger the pull of gravity on the pendulum, the shorter it will take to swing back and forth between each one. Now let's take a look at our springs. Now, springs, virtually the same equation. 2 pi times the square root of m over k equals our period. And again, let's take a look at what is and what isn't in this equation. This equation does not include the length of the spring. It only includes mass, the spring constant, and the period itself. Further, our mass is in the numerator, which means the bigger the mass, the longer it will take to go all the way back and forth. And the k is in the denominator, so the bigger the k, the smaller this gets. So the stiffer the spring, the faster it will flip back and forth. Okay, and then one that applies for both of these is that lowercase f is equal to 1 over our t. Now, our period is equal to our number of seconds, or our small t, divided by our number of revolutions. Because what we want this to be in is seconds per revolution, how long it takes to complete one revolution. Our frequency, since it is the reciprocal of our period, is actually the number of oscillations in however much time, or revolutions per second, which we also call hertz. Okay, cool. Let's go ahead and do a couple problems. Okay, let's start with a hard one. Okay, so an astronaut has been in space for a long time. He doesn't know how much his mass is right now, but when he steps off his spaceship, he steps onto a oddly placed bathroom scale and finds that he weighs 200 newtons. Say he weighs 200 newtons. He happens to have one of those apparatus that we discussed at the beginning of this unit, where he uses a spring to determine his mass. Okay, and let's assume that the spring has a known K of 80 newtons per meter. He gets on it and it oscillates at a frequency of 1/4 hertz. How much is his mass, or what is his, what is his mass? What's G on this planet? And what is period? There we go. That's plenty of stuff right there to get going with. Okay. So easiest thing is going to be calculating our period. That's just 1 over F, or 1 over 0.25. And that's just 4 seconds. All right. That was bad. Bad handwriting. 4 seconds. Okay? That's what that is. Easy peasy. Next, let's see which we can calculate. So we have our T. Let's go ahead and say, what would our X be if he just sat on our spring? Okay, so M over K. There we go. Boom. There's our equation right now. Now we are given K, and we've calculated our period. We don't know our mass, but that's what we're trying to figure out. Okay, so we need to rearrange this equation so that mass jumps out at us. So we need to get rid of 2 pi on this side, so we have to divide both sides by 2 pi. So T 2 pi equals square root of M over K. Square root both sides. We have T squared equals 4 pi squared equals M over K. And now we can multiply both sides by K. So M is equal to T squared K over 4 pi squared. Okay, feel free to correct any mistakes you see, but I think we're good. So 4 squared times 80 divided by 4 pi squared should be our mass. So 16 times 80 divided by 4 divided by pi divided by pi. So we have a mass of 32.42 kilograms. Now that is way low for an astronaut. An adult human of any kind would be really pressed to be only about 70 pounds. But you know, I made these numbers up, so don't hassle me. So 32.42 kg. Next, we already found out our period. 4 seconds. All right, next, let's see what our G is on this planet. Now, we know F is equal to mg, if we're talking about weight. We know our M, we know our F, we don't know our G. So G is equal to F divided by M, or 200 divided by 32.42. Or a total of 6.17 meters per second squared. And then last, let's see what it would be if we just compress the spring with the weight of the astronaut. Let's see how much he would weigh, he or she, I guess. So we should remember that F equals kx. We know our F, which is 200 newtons. We know our K, which is 80 newtons per meter. And we're looking for an X in meters. So we divide both sides by 80. And we end up with 200 divided by 80. An X of 2.5 meters. That is a long spring. Okay, there we go. That is everything for this problem. Let's go ahead and move on. Okay. Okay, so we have a pendulum that is 2 meters long. We have a mass hanging from it that is 0.5 kilograms. This pendulum has a period of 3 seconds. I want to know what G is on this, wherever this place is, and I want to know the weight All right. Okay. Let's see what we got. All right. So we have our period, and we have our period, our mass, and our length. You should immediately recognize that mass does not matter to the period of a pendulum. But let's go ahead and talk about it anyway. So period of a pendulum is 2 pi times the square root of L over G. Now we know our period, we know our L, we don't know our G. So let's divide both sides by 2 pi. And square both sides. So t squared over 4 pi squared equals L over G. Now we need to take the reciprocal of both sides. So G over L equals 4 pi squared over t squared. And lastly, let's multiply both sides by L to get rid of that L down there in the bottom. So G is equal to 4 pi squared L over t squared. And that we know everything, or know enough to do our math. So pi squared times 4 times 2 for the L divided by t squared, or 3 squared, so 9. So our G on this planet is 8.77 meters per second squared. So that's our G. Boom. Easy. Yes, I'm still at school. Next, we need to find out our force. And this is just a reminder, but F equals mg, and our mass is 0.5 kg times our 8.77 meters per second squared, or a weight of 4.386 newtons. Cool. Okay, let's do one more spring one. Okay, so now we're not going to do energy with it. Okay, so we have a 2 kilogram mass attached to a vertical spring, and the stretch of the spring is a total of 0.5 meters. I want to know what K is, what the period is, and what the frequency is. Okay, cool. And this will be my last one. Okay, so first things first, let's go ahead and assume, well, let's go ahead and explicitly state Earth. So our G, we do know one more thing. G is 9.8 meters per second squared. Okay, cool. So our force pulling down on the spring to start with is mg, or 2 kilograms times 9.8 meters per second squared, or 19.6 newtons, okay? F is also equal to kx, but we're solving for k, so divide both sides by x. K is equal to F over x, or 19.6 divided by 0.5, or times 2, 39.2 newtons per meter. Boom, there we go. Actually, let me make sure I did that right. Yep. So K is pretty easy. And now, same deal, second verse, same as the first. T is equal to 2 pi m over k. I know it looks like I almost drew a G there, and I did, but it is a K. Solve for the length and period of a pendulum. All right, yeah, I can do one more. All right, so we know enough. Let's plug this in. 2 pi times the square root of 2 divided by 39.2. So square root that times 2 times pi. So our period ends up being 1.419 seconds. And frequency is just 1 over t, so 1 over 1.419. Boom. Our frequency is 0.705 hertz. Box. All right. And then one more. Okay. We can't solve for length and period. We would have to have some way of knowing the length or the period. Both of those are in the same. Now, the period is pretty easy. Here's the equation, L over G. So we just need to have these two pieces and you can calculate this. Okay. Now, normally, if we're asking you to calculate G, or if it's someplace other than Earth, we're going to give you some piece of information like the weight of an object with a known mass, for which you can solve G, or we'll tell you T, and then you can solve backwards for G. But I can do a problem that solves for L. Let's do one that solves for. Let's just plug one in. Okay, so if a pendulum is 1 meter long, what's its period? So T equals, and again, if it doesn't give you anything else, then we're going to assume Earth. There we go. T equals 2 pi times the square root of L over G. So 2 pi times the square root of 1 over 9.8. Or and that, if we just plug all that in, that gives us 2.01 seconds for the period of a pendulum that long. But now, if we had a pendulum with a period of 4 seconds, what would its length be? I don't know what that sound is. Oh well. So again, all right. T equals 2 pi times the square root of L over G. Now we're trying to get L out by himself again. So divide both sides by 2 pi and square both sides. T squared over 4 pi squared equals L over G. Multiply both sides by G. We end up with L equals G T squared over 4 pi squared, or T squared G, whatever. And again, we know our period and we know our G. So 9.8 times 4 squared, which is 16, divided by 4 pi squared. And plug that in. 9.8 times 16 divided by 4 divided by pi divided by pi. So our length in that case would have to be 3.97 meters. Okay? Okay, so all of that seemed pretty straightforward. Why do you put the t squared together with the g? Okay, so when I was up here doing algebra to get L all by himself, I had to get rid of this g down here in the denominator. The only way to do that is to multiply both sides by g. And by multiplying by g rather than dividing, this g ends up in the numerator. So g times t squared equal over 4 pi squared. That's how that works out. That's just regular old algebra. Okay, good. Now, I hope this was helpful, and I'll see you in class. Good luck tomorrow.